right. So the plan today is pretty straightforward. Not a lot of, secrets going on here. We've got homework to go over if there are questions. I've got some ranking tasks to work on, some other just kind of conservation of energy practice problem stuff. That'll get us through the day, I think, because it's a not extremely long day. And then we're going to review tomorrow. I would strongly encourage you to bring questions if you have them tomorrow. Tomorrow is our last day before our test, which will be on Thursday. Is that right? Am I doing this right? Yeah, because we're not going to test tomorrow. We were planning to test Thursday, right? Is that correct? Nick's just going to say no regardless of what I ask. We're going to test on Thursday. We're going to review tomorrow. It'll be great. All right, so first question for you all. Do you have questions over the homework that you would like to discuss? Yes? Yes? All right. So I'm going to get out a new page, and you're going to get your homework out and close your mouth so that it's not loud and distracting. All right. So what questions do you have? What can we do? 24, 28, and 29? Okay. So lots of spring questions, is that right? Okay. Oh, 29 is not. Yeah. Good. Yeah, it is. Yeah. All right. So a friendly reminder to my friends who have done their homework and who are just waiting quietly because they already know all the answers. Please sit and wait quietly so that you're not distracting me while I'm talking to those people that need some help. All right. So the 3 requests that I've had right now are 24, 28, 29. Anybody want to put anything else out there right now?
Is this the last homework assignment?
This is the last book homework assignment that you have. There's one more thing I'm going to give you today. Yeah. 41 and 12? Sure. No.
Not 12.
Oh, and what? And I meant 27. Just said 41. You said 41. So, okay, 40 and 27. Okay. Yeah, I was talking to both of you at the same time in some sort of magical way that I'm not good at, apparently. All right, so I'm going to start with question 27. Is that okay? Yes. And then we'll move on from there. Going through things kind of in order maybe makes sense? Okay, so question 27. So again, if you have not done your homework, this is a great time to write it down. If you have done your homework, this is a great time to make sure you're on the right track. And if you totally understand it, then just don't be distracting to the rest of us. Thanks. All right. So question 27 says, a hockey puck sliding along frictionless ice with a speed v to the right collides with a horizontal spring and compresses it by 2 centimeters before coming to a momentary stop. What will the spring's maximum compression be if the same puck hits it at a speed of 2v? This is like the quintessential AP Physics question, right? Because there aren't really any numbers, but they want to know if you understand physics. Okay, so that is it right there. So talk to me. I'm not going to tell you how to do it. I want to know from you, how are you going to set this up? What are you going to do?
Well, I tried to use conservation of energy.
That seems like a reasonable choice. So what kind of energies do we have involved in this story?
Don't we have kinetic and wait, you said hockey? God, yeah. That would be thermal energy. I think I wrote spring.
It is spring. No, it's spring. Yeah.
Okay, yeah,
yep, it's on a nearly frictionless surface, so there's no heat.
Spring.
Yep.
Right.
Yep.
That's what I meant to say.
So this is the initial part, and this is the final part. So at the beginning, what kind of energy does that hockey puck have?
Kinetic.
Just kinetic, straight up only kinetic, right? So this is 1/2 mv initial squared. And at the end, so just to get your head around kind of what's happening here, so we got this little hockey puck, right? And it's moving, and then it's going to hit a spring that just happens to be attached to the edge of the rink, I guess. I don't know. It's not something I'm familiar with, but whatever works for you. And so then it's going to go and it's going to compress that spring. So the spring now is squeezed up like this, and the hockey puck is here. And is it moving?
No.
No, it's not moving anymore. So what kind of energy does it have then?
Spring potential.
only spring potential, no more kinetic. And we can quantify the amount of spring potential energy, can't we? We did that yesterday. We derived it yesterday. What did you get?
1.5 K.
Mm-hmm. So this is the situation in both cases. Hi. Yes, of course.
Okay, guys, so
Good.
we've got the 1/2. So I think we go to what? No.
Hey! Henry.
Stop. Dude, come on.
Welcome to
What's
live
the
on.
point of that?
Henry, sit down.
Sit down. Trying to
Yeah,
get
Henry, the whole side.
the
Stop it.
All right, because it's sorry about that. Okay, here we go. Whew. All right, so this is a situation regardless of what else is going on. Okay?
Yeah.
And so now we've got two situations. We've got, in case A or in case 1 or whatever we want to call it, we'll call it case A. We've got an initial speed is just V. That's what they call it, right? And the distance that it travels or the distance that it compresses is 2 centimeters. And then they're saying, okay, what about in case B? And in case B, they want to know if the initial velocity is now 2v, what's going to happen to x? How do we do that? So really, this is an opportunity to look at the relationship between kinetic energy and spring potential energy. We could, yeah. Let's do that. Before we do that, though, I want you to look at this and see if you can come up with a gut feeling here. What do you think might happen? It's a gut feeling? Let's plug it in and find out. So, when you say to plug it in, Jasmine, what do you mean? What do you want me to write?
How I did it, I just put V in and 2 centimeters in for case A, so 1/2 mv squared equals 1/2 times K times 2 squared.
Okay.
And or I did a little differently, but okay, so 1/2 mv squared equals 2K. And then you do the same for case B.
Okay. So you've got, in this case, 1/2 m times 2v squared equals 1/2 k x squared. And so now we're trying to figure out what x is going to be, right? So that's kind of what I'm thinking. I'm thinking if we can get this side here to look like this side here, then we can get a sense of what's going to happen. Let me show you what I mean. If instead of writing this as 1/2 m times 2v squared, what if I apply this squared to everything in here?
Let's do it.
That means we're going to get 1/2 m times 4v squared. Is that okay?
Yep.
I could write that as 4 times 1/2 m v squared. Is that okay? So that means that by doubling the velocity, I have 4 times the kinetic energy. Okay? So I got 4 times the kinetic energy, which means that I've got to have 4 times the spring potential energy. Okay? So that means that I'm going to have 4 times, so it's going to equal 4 times the 1/2 k times, oops, that's ugly, 2 squared thing. Because this one is the same as that there. I have 4 times the left-hand side, so I have to have 4 times the right-hand side as well.
Right.
4 times the right-hand side as well. But now I want this to just look like that, so I want to know what x is going to be.
Bless you.
Does that make, are we okay so far? I want to know what my x value would be. So let me set it up like this. This thing here, 1/2 kx squared is equal to 4 times 1/2 k times 2 squared. There's a 1/2 k in both of those, isn't it? Let's get rid of the 1/2 k to make my life happier. X squared equals 4 times 2 squared. Two squared is 4. 4 times 4 is 16. X squared equals 16. So what does x equal? 4. How does 4 compare to the original 2? It's twice as big. So Isaac's instinct was right. It's exciting, right? It's exciting when your instinct is right. The reason that your instinct was right in this case, but it might not always be. So in the case of the way that this is written, so the answer is going to be C. The reason that it works though, friends, and the thing that I want to point out to you, because it doesn't always work this way, well, in this case it would, but not always. If you double one side, the other side's going to double. The reason that it works this way is that both V and X are squared. Okay. We've done problems like this very recently where you've had like an object that's going down a hill, like on a roller coaster, right? And by doubling the speed, that doesn't double the height.
Well, but isn't that because of the types of energies involved?
So from a physics perspective, yes. From like a purely math perspective, no. Because it's just that you got one that's squared and one that's not squared. Like in the like MGH and 1/2 MV squared when we do that problem, then if this one's doubled, then the other one has to be 4 times, has to be quadrupled.
Yeah, that's what I mean.
Yes.
Because they're doubled, because of the types of energy, they are doubled. So
Yes.
That's why, or
So
squared, I mean.
yes.
So
So yes is the answer to that question.
cool.
Yeah.
Can we go down real quick one time so I can see it?
Sure, of course. Is that where you wanted to look?
Where'd the 4 go? There was a 4 on the left side, now there's not a 4.
Here?
Yeah. I don't know.
So this was just me saying, okay, so I've got 4 times the initial, so I've got to have 4 times the final. So this 4 is right here. So all I'm doing is I'm taking this. This is one expression for the after, and this is another expression for the after, and I'm trying to solve for x.
Yes, I understand.
Is that okay?
Yes.
Okay. All right. Can we move on?
Yeah.
Yeah, problem.
Are you just being facetious? Okay. Or
I actually get it now.
what'd you say? Like, should I really listen to you or can I move on? Is that okay?
Be free.
24, let's look at it. This is problem 24. How far must you stretch a spring with a spring constant of 1,000 newtons per meter in order to store 200 joules of energy? So U sub S is equal to 1/2 kx squared. We're just solving for x there, friends. So you got 200 joules of energy equals 1/2 times 1,000 times x squared, solve for x. Is that okay? Unless I missed something. Are we okay on that one?
Yeah.
Do we get an answer? I don't know what the answer is off the top of my head. 400 divided by 1,000? Square rooted? 28. Oh, the scallops. You guys like those bio examples? No. Do I have any biologists in here? People that love bio?
I do.
Yeah, a few of you?
My dad's a brain doctor.
That's awesome. My parents were pharmacists, but I have no interest in pharmacy, so I don't want to make assumptions. All right. Scallops use their muscles to open and close their shells. To close their shells. Opening the shell is another story. Mussels can only pull, they can't push. Instead of muscles, the shell is opened by a spring. That's so interesting. A pad of very elastic biological material called an abductin. When the shell closes, the pad compresses. A restoring force then pushes the shell back open. The energy to open the shell comes from the elastic energy stored in the shell when it was closed. Okay, that's a lot of information. The picture shows a line for the restoring force of abductin pad versus the compression. Okay, so we've got a graph. It goes up to 2.5 newtons, force in newtons. When it gets to 0.2 distance in millimeters. Whoa. Da-ding. All right. When the shell closes, the pad compresses a distance of 0.15 millimeters. What is the elastic potential energy? So US equals question mark. All right. So there's a lot of information to kind of wade through here, right? But all in all, this should be a pretty straightforward question. What information can you get from this graph? You can get the force at a certain distance, and you remember from this graph, we said that F was equal to Kx, right? It's just a line, y equals mx plus b, right? Where the y is F, the k is m, and the x is x. There's no b. So if you can find the slope of this line, then you know your spring constant. Okay? AP likes that a lot too. Here, I'm just going to throw a graph at you, and I'm going to see if you know what to do with it, right? So that means you have to understand the physics behind what they're showing you. So if you see a force versus distance graph, okay, you know it's got to have something to do with work. That's got to have something to do with, if it's a spring situation, then finding a K. So you have to find the slope, right? Find the slope of that line, that'll give you K. And then,
Wait, what's that?
Go ahead. Question?
What's X? Sorry.
Distance? So once you found this spring constant, it tells you that it has been displaced to a distance of 0.15 millimeters. And then you can solve for spring energy. Is that okay? Did I throw you off? Are we okay? Help me out.
We got another step.
Sure. So how do you find the slope of a line?
Rise of run.
Yeah, you do. So let's find K. Rise over run. So we've got 0, 0 as a point, and we've got 0.2, 2.5 as a point. Can you find the slope of those two things? Or those points? Sure. Yeah. It's going to be 2.5 newtons per 0.2 meters. 12.5. That's millimeters, isn't it? I think. Newtons per millimeter.
Yeah.
You can leave it all in millimeters because this is going to be in millimeters as well. I think you'll be okay. Well, you probably want to convert it. I don't know how they answered it. Probably want to convert it.
So that's
K.
the spring constant, yeah.
Yep. And then you've got your distance of 0.15 millimeters.
Yeah.
I think in order to get it in joules, and because joules has meters, you need to convert them all to meters. But that's just moving it over 3, right? You got that.
You can give your answer in voltages.
You could. I mean, yes, you could.
Zero.
So they're going to be little. Yes. Yes. So it's going to be 0.15 times 10 to the negative 3. So 1.5 times 10 to the negative 4. Did you have a question, Courtney?
No, I was just.
Okay, 0.
How are we doing, team? Are we okay?
So when you make like the triangle on this graph,
Yeah.
the area of that is the work.
That is the work that's done over the 0.2.
Yeah.
So you could also, do they have a point for, yeah, you could also just find the area under that. That would work too.
That's a lot of.
Yeah. Did you guys catch what Nick just asked? He said, oh, or you could, I didn't even think about doing that way. Just come over here to where it intersects the 0.15. And the area under that part of the curve would be the work as well. Change of potential energy. That's clever. I think that would work. Or that would.
Wait, but
Yeah, it is. It's just doing it in a different way.
so, but how would you do that? You go to the.
So because the distance was not 0.2, it was only 0.15. So
Okay.
the little spring is being stretched 0.15 millimeters.
Mm-hmm.
So the work done is just the area under that triangle.
But then, how would you know how far to go up for like the?
Because there is data. Like it's on the graph.
Oh yeah.
Yep. So it goes to what is it? 2. It's close. It's not exact. It's harder to see. I thought it intersected exactly, but it doesn't quite. It's just a little less than 2. So it's like 1.95 or something. Something to that effect. Yeah. But that's another good way to look at it. All right, can we keep cruising?
Yeah.
Yeah. Let's keep going. That's 28. How about 29? Who was excited about 29? Somebody was.
It was.
Let's do 29. There are people that want to do 29, right? True? Okay, awesome. Mark pushes his broken car 150 meters down the block to his friend's house. He has to exert a 110 Newton force to push the car at a constant speed. At a constant speed. Hey, the speed is constant. What does that tell us?
That's 0.
Oh, that's important to know, isn't it? Yeah. How much thermal energy is created? So here's the car, right? Here's the force of Mark. His name is Mark, right? Mark on the car. And if the speed is constant, that means the net force has to be 0. That means that there's also a force of the surface on the car, and that is the frictional force, right? It says that the car travels a distance of 150 meters, and Mark exerts a force of 110 newtons on the car. So how big is the frictional force? Negative 110, right? And so the thermal energy, E sub TH, is just going to be the force that's applied over the distance that it's applied, right? The force of friction applied over that distance. You got this. Does that make sense? Just do some multiplication.
But so.
Go ahead. I'm listening.
But right. That's it. So it would just be positive, right? Because you're not.
Yeah, because you're just talking about the amount of energy. Yeah, yeah. How much thermal energy is created. Yep.
The units are.
Joules. Yeah, because it's always, energy is always measured in joules. But it's a force times the distance, which is the same as work, which is also joules. Yeah. It's all just joules. All right, keep cruising. Yes, please. All right. Last one here, friends. 41. Ooh. Oh, we don't even have to turn the page. Oh, yeah. The firefighter. Firefighter with a mass of 80 kilograms. Slides down a pole. When he reaches the bottom, 4.2 meters below his starting point. His speed is 2.2 meters per second. How much thermal energy has been generated, or by how much has the thermal energy increased during the slide? So here's the person here. Yay! And then here's the person here. Not drawn to scale, right? Yay! All right, so there they are. So let me not say at the top. In this story, what kinds of energy are we dealing with? Name one of them.
Potential.
Gravitational potential. What else we got?
Thermal.
Thermal. What else we got?
Kinetic.
All right.
But not spring.
We don't have any springs involved. All right. So we're just going to write it out. Conservation of energy says that the energy at the top has to be equal to the energy at the bottom. So this is at the top. This is at the bottom. Talk to me about what kinds of energy exist in any given place.
At the top, the potential. There's no kinetic at the top.
There's no kinetic at the top? How do we know that?
Because you told us.
Because we assume that it's not moving, right? Yep. They're just going to say, okay, yep, boom. So there's no kinetic.
And then at the bottom, there's no gravitation.
There's no gravitation at the bottom. And I heard something else coming from over here, but I don't know who it was. No thermal energy because he hasn't moved at all, right? It's force times distance. So there's no thermal energy at the beginning. So we got just gravitational potential at the top. We've got thermal and kinetic at the bottom. And which one are we trying to find?
No thermal.
This one here, right? We don't need to know the force or anything like that. All we need to know is what is that value. So mgh at the top equals ETH plus 1/2 MV final squared. Okay. When you're taking a test over this material, if you happen to have a problem like this, if you just have this written, I will not give you full credit. I need a statement of conservation of energy that is clear, okay? That is clear, that says, I know all the kinds of energy at the beginning and the end have to add up to the same thing, okay? Just starting here is not okay because it's not explicit enough, all right? Okay, all right. So you know his mass? Do we know his mass? Yep, I wrote it down even, okay? We know the height. Yep, 4.2. We know the mass, we know the velocity. So down here he has a velocity of 2.2. And then we get to solve, yeah? How are we doing?
Pretty good.
Do we need some more help or are we doing okay? All right. Other homework questions before we move on? I've just got a bunch of problems for us to work in the next 14 minutes. Is that okay?
Yeah.
All right. I'm going to throw the first one on the board right now. Here it comes.
Oh.
It's Kathleen, I know. It's a little disappointing there. All right. 2 water slides at a pool are shaped differently, but they start at the same height. 2 riders, Paul and Kathleen, start from rest at the same time. Question 1, which rider, Paul or Kathleen, is traveling faster at the bottom? And part 2, which rider makes it to the bottom first?
Obviously, Catherine.
So go ahead and take a look at this. Talk to your table mates. Have a conversation.
Paul. That's what I have. No, anyway, just switched them. Paul. He's using more than kinetic energy.
Okay.
24.
Plateau and then
Right, let's do this.
Don't play with her. Oh, I miss
Oh, no, no,
keys.
it's her.
Rudy's.
There we go. All right, let's do it. What's the right answer?
Neither is traveling faster. Right.
They're traveling the same speed. Yeah.
Well, that's what it means. They're both traveling together. Because at the bottom.
You guys all agree?
We have the same.
It's like our good old marble. Marble roofs.
They're true.
Anybody disagree with that? Cole, what did you say? Say that again. What you just said.
They have the same total energy, and so they'll have the same kinetic energy at the bottom.
Yeah. Cool. Which one has more potential energy at the top?
No, it's the same. At the start, it's the same.
Here.
The top is the same.
Yeah, it's the same.
Oh, yeah,
potential.
it's the same.
Well, wait. Doesn't it?
What'd you say?
Or we assuming false.
We don't know, do we?
Depends on their.
We'll say quality.
Or
So if we assume, because social convention teaches us to, if we assume that Paul has more mass, then Paul is going to have more potential energy at the top, right? Who's going to have more kinetic energy at the bottom?
Paul.
If we make that assumption. So that's a really important distinction to make, right? We know that even though they have the same speed, we know that they're going to have different potential energies and therefore different kinetic energies if they have different masses. If they're the same mass, then it's just, all a wash. Okay? Who's going to make it to the bottom first?
obviously Kathleen.
Yeah.
Oh.
No, you're wrong.
False.
I already know everything.
So Henry, tell me why you are voting for Kathleen.
She gets rid of the potential energy the fastest.
Tell me, I don't understand what you mean. Say more.
All right, so basically this was going on. Paul's the top,
in a
right?
normal voice.
He's chilling, and he's going down. And then Kathleen, but she go down faster, so she loses potential energy quicker.
So if she loses potential energy faster, that means that she gains
Kinetic.
kinetic energy faster, which means that she's traveling during this part down here. She's moving faster than Paul is, right? Absolutely. Yep. So even though they'll have the same speed at the bottom, she spends more time going faster. So she will travel that horizontal distance faster. Sweet. All right. How about this one? Shown are blocks that are sliding down a frictionless incline, so no thermal energy in here, friends. All the masses start from rest at the top of an incline. It asks you to rank the kinetic energy of the sliding masses the instant that they reach the bottom of the incline. Go ahead. All right. So let me see some boards. Well, if you move them, I can't. Face-ebbed?
Face bed.
Face-bed.
But you can add the
Okay, so there are some that are in disagreements. All right, talk to me, friends. I see some things that agree and some things that don't. Talk to me. What did you do? How did you figure it out? Start us off, Nick.
There's only two types of energy. There's potential and kinetic. And so basically whatever the potential is at the very top, that's what the kinetic will be at the bottom.
Does that seem reasonable?
Yes.
I did.
Sweet. And so we're going to talk about the potential at the top. So that's going to be M times G times H. So what things do you need to take into account then?
The mass and the height.
Mass and the height? So we just need to multiply them together, right?
Right.
So like A is going to be 10.
Yep.
I can do that one in my head. And B is going to be 2. And C is going to be, and D is going to be,
1.5.
and E,
20 or 2.5.
and F.
11.
45 fourths.
Whoa. What? Did you say 4?
He said 45 fourths. 11.25. All right. So that means F and then A and C and then E, B, and then D?
Yep.
All right.
Can you write it as a mixed number, please?
No.
Jasmine likes mixed numbers.
That's great.
No.
Here's another one.
Now you can take over the board. I just got
This is good review stuff here, friends. Go ahead.
Okay.
Ooh.
Right?
In the figures below, identical boxes of mass 10 kilograms are moving at the same initial velocity to the right on a flat surface. The same magnitude force is applied to each box for the distance indicated. The question says to rank the work done on the box by F while it moves that distance. So in all cases, the box is moving that distance. Okay? I just want to know the work done by the force as that box moves. Okay?
So
Just before the bell's gonna ring.
Are we on soft lockdown?
What?
That's what Kate's mom said.
We got an email.
People threatened Tate High School, so
All
now.
right. What do we got? What do we got?
face step.
You say B, A, E, C, D, F. Do you guys all agree on that?
They don't.
We can't
Hey, don't need to figure us out now.
No. I just want to know. So why are you saying that B is the biggest?
Because it has
the greatest distance.
Yeah. So force times distance. So that one compared to A is also going in the same direction, but for not as big of a distance. And then you said E.
equal to E, yeah.
How though?
No, he is.
So how do A and E compare?
They
They're the
don't.
same distance.
It's the same force, but one is parallel and one is anti-parallel, right? Yeah. So I would call this a negative.
Yeah.
I would call that one a negative.
Oh,
Yep.
so you're right. You're
So
right.
I would say B, A, C, D, and F are the same, and then E.
Dude,
That's what I would say.
Wait, I was thinking magnitude.
Yeah, it doesn't say that, though, silly thing. I know, right?
Well, then I would have had to. But I